baseband transmission through AWGN channel. What is an AWGN channel? What is an AWGN channel? What is Gaussian distribution, normal distribution? And why is Gaussian distribution so important? What is meant by Gaussian distribution and why Gaussian distribution is very important? You have studied 2 years of mathematics, right? Engineering mathematics. So tell me what is Gaussian distribution and why Gaussian distribution is important. If you have studied for 2 years and your teachers have taught you what is Gaussian maths basics, you should have now been able to explain to me why Gaussian distribution is very important. Any one of you in this class, can you tell me what do you understand by Gaussian distribution and why Gaussian distribution is very important? You might have studied probability distribution in your previous semesters, right? Yes or no? Probability distributions, how many of you have not studied? Come on, let me know. So, Gaussian distribution is a distribution which appears like this. Okay, it is symmetric about the mean. Right, this point is called mean. Why Gaussian distribution is important? Because most of the things, objects or whatever you find inside is a Gaussian distribution. Suppose you take the height of the students in your class. There will be some people, very small people, there will be tall people, and then there will be very tall people. Right? Yes or no? Now all of you are able to understand what is Gaussian distribution, which you are expected to know when you have passed your 12th standard. Manslaya, all of you, you understood why Gaussian distribution is important, because most of the events that happen or most of the probability distributions are distributed in such a way that it starts from small, goes to big, and there will be a peak, and then it will come down. More tall people will be there, more height marks, anything you take is a Gaussian distribution. There will be few people who score 0 marks in internals. There will be few people who score 100 out of 100 in internals. Right? But those who score 0 will be very few. Those who score 100 also will be very few. But most of them will be in the mid range, this range. Okay? So tomorrow you are asked why Gaussian distribution is important. Don't tell I don't know. Is it clear? Is there anybody in this class who did not understand what is Gaussian distribution? Raise your hands. Good. I hope all of you understood. So AWGN channel means additive wide Gaussian channel. Okay. So we expect our signal powers to be also following the probability distribution function of PDF of a normal or a Gaussian distribution, right? So Gaussian is clear, all of you? White additive. Additive means you are adding the noise through the channel. You are expecting a baseband transmission in which you are adding a Gaussian noise. So noise is also expected to be a Gaussian. If you imagine it in a three-dimensional space, you will have it as a Gaussian distribution with zero mean and one variance. Okay, so this is what is meant by baseband transmission. This is what is meant by white Gaussian noise that is being added to the original signal when you transmit. So write down what is meant by baseband transmission and what is that you are going to study. So basically digital data, you need to have a sinusoidal or some kind of signal that is going to carry your digital values. There is no direct digital transmission without any carrier signals. Okay, those signals that is being transmitted without any sinusoidal waves are called as baseband signals, and they have generally a low frequency content because it is completely digital. And the next point here is that the digital data gets modulated with the help of a sinusoidal carrier, and modulated band pass is transmitted. That is called as band pass transmission. So there are two types, baseband and band pass. Baseband signals are those signals that do not have any sinusoidal signal with them. Okay. Baseband transmission through AWGN channel will be transmitting symbols and only symbols. So this slide tells you what is a binary baseband and a M-array baseband signals. Generally we have two values, 0 and 1. We call it as binary. Sometimes for the sake of our estimation and calculation, we may use -1 and 1 or minus A and A. So in binary baseband transmission, there are only two possible values. One is the A and the other one is minus A or 0. In M-array, we have M possible values. So binary input data can take n values bk. We have a pulse amplitude modulator, transmit, filter, channel, and then you are adding the white Gaussian noise. This is what is called as baseband transmission through AWGN. And in the receiver filter, you are receiving the filter and then you are having a decision device to make out the bit for that. So now, in the block diagram which you have drawn in the previous slide, there is no, you could have noticed that there is no carrier modulation in the transmitter, and so there is no demodulation process also in the receiver. And for K values, the pulse amplitude modulator changes the input binary data stream into a sequence of short pulses. So the sequence of short pulses produced is applied to the transmit filter here, G of t with the transfer function G of t. The transmitted signal is now defined as S of t is equal to sigma k ak G of t minus k tb. A very important definition of what is an intersymbol interference. A very common question that is asked in all your vivas, interviews and everywhere. What do you understand by intersymbol interference and why does it occur? Intersymbol interference means I'll explain to you what is an intersymbol interference. If you listen to me, you can understand it very easily. There is a pulse that is being transmitted. Okay, you have a neighboring another one pulse. While traveling in the channel, after this, if you have one pulse overlapping over the other due to any kind of time delay, this phenomenon is called as intersymbol interference. Okay, when one pulse while traveling faces any kind of time delay and is not able to reach in time or is able to overlap with the adjacent pulse, it is called as intersymbol interference. Okay, understood all of you? So let us study what is the mathematical modeling or how do we understand intersymbol interference through mathematical equations. So from the explanation of the previous slide, you would have understood that intersymbol interference is something that is not desirable. It is a noise or is something a kind of disturbance, right? So what we have to do, we have to take steps to eliminate this kind of interference. So this slide tells you that this is a form of distortion in the signal where the first symbol interferes with the next symbol. So it means that there is a kind of, say, symbols means you have the last. Okay. So I told you that we have no, in a symbol you will be having multiple bits. So each of these will be bits. So this can have 0 and this can have 1. So what happens is that there would be a change in the value as such, which is a distortion. So one symbol interferes with its subsequent symbols. So this is an undesirable phenomenon and this is caused because of time delay, the spreading of the pulse beyond its allotted time interval. So what is the cost for intersymbol interference? A very common question that comes in your exams. Why does intersymbol interference occur? Tell me. Time delay. Good. The signal gets spread over to the next pulse, right? So that's the reason for intersymbol interference. Every of my slide is an answer to a university question. Okay, keep this point in mind. This question says that give us the two important considerations while designing a physical communication channel. So these are the two important considerations. One is the intersymbol interference and the second one is the channel noise. And this was a question that was asked in our previous year paper. So transmission of digital data, you have two important considerations. The first consideration is called as intersymbol interference. The second one is the channel noise. Channel noise is this unwanted signals that arise at the channel output due to the random and unpredictable physical phenomena. So this is the input signal. Baseband we have already seen. S of t is equal to the summation of all up to k, ak, transfer function of the transmit signal. The scaled pulse, after you have the pulse amplitude modulation here, the scaled pulse is obtained by double convolution involving impulse response g of t of the transmit filter. The impulse response h of t of the channel and the impulse response c of t of the receive filter. So what is p of t? G of t convolution h of t convolution c of t. So from the previous equation, so here we get the output symbol of the received one as YTI, okay, which is nothing but the summation of k is equal to minus, we don't know how long it goes on. Suppose you are transmitting a voice signal, it can start from 0 to minus infinity to infinity or something beyond. So we have a input signal A of k, which will be P of I minus k TB. So this is the ith symbol. Okay. So this gives you the output at the ith of the ith symbol at the receiver. So let's look into this derivation in detail. The first term AFI represents the contribution of the ith transmitted bit. So the next term here represents the residual of all other transmitted bits on decoding of the ith bit. And this residual effect is mathematically defined as the intersymbol interference. So when you don't have any intersymbol interference, your output for the ith symbol yt of I will be A of I. If you do not have any intersymbol interference, yt of I will be equal to A of I. So what does the word baseband mean? Baseband is a range of frequencies from where the original signal can be delivered. The source of information here could be a stream of binary data made up of symbols of zeros and ones. So this is what is meant by baseband. So let us now consider two pulses like this with pulse TB and with TB. So let us consider the output pulse which is having a Gaussian distribution or something very similar to the Gaussian one. We have two data, one for 0 and one for 1 and the other one for 0. So we'll be learning the techniques to avoid intersymbol interference. So when you represent the channel characteristics with a graphical note, you can note that the signal that is transmitted at the transmitter is received with another kind of pulse that can support or help us in reduction of intersymbol interference. So in the mathematical model, we are considering three parts. The transmitting filter with a transfer function h f of f, the channel hc and the receiver hr. Okay, the signal at the output will consist of the convolution. We have seen this in the previous slide itself, that it is a double convolution of the three important characteristics, that is the transmission characteristics, channel characteristics, and the receiver characteristics. Okay, and we'll be having respective weights for each of these things. So this is the block diagram of the entire system, which we have seen in different parts. The complete system integrated together, both the transmitter, receiver, and the channel. So this is consisting of the input data dk with k symbols, pulse generator to generate pulse with a transfer function of gt of t, and a transmitting filter, noiseless channel, passing through an additive white Gaussian noise. See, this symbol here is plus. That means additive means the noise is added to the signal. Okay, that is why we consider it to be AWGN. In most cases, the noise is additive white Gaussian noise. After the channel, it goes through the receiving filter and then to the decision device to get the proper output. So with this, we will be concluding on the mathematical model for intersymbol interference and baseband transmission. The next class, we will see what is Nyquist criteria for intersymbol interference.